Okay, welcome back, ladies and gentlemen. This is the lecture on section 5-2. 5-2. This is recording number 1. We'll see if I need to do more than one. So we in 5-1, we talked about probability distributions. So we're in chapter 5, so we're talking about probability distributions, but specifically we're talking about discrete probability distribution. Now the word discrete refers to what kind of a variable are we talking about? What kind of a random variable? Is it a discrete random variable or is it a continuous random variable? That's the main way we distinguish or we place these probability distributions into a category. It's either discrete or it's continuous. Chapter 5, we're talking about discrete probability distributions. All right, so that was 5-1. Now we're going to jump into 5-2. Now 5-2, you look at the outline here, and it looks very similar to what we've talked about before, mean, variance, and so forth. Okay, now as I mentioned to you before, chapter 3 talked about frequency distributions. That's actual data. Those are events that have happened. You've measured them. You've taken the measurements already. Chapter 5, we're talking about probability. It hasn't happened yet. We are talking about what is the probability that something is going to happen. What do we expect to have happen? So it's the difference between descriptive statistics and inferential statistics. These terms or these concepts, mean, variance, and so forth, are going to sound very similar to what we've already talked about. However, there are some differences, so you need to definitely pay attention to the distinction, okay? So we've got the objectives here. As usual, I strongly urge you to read that carefully, and as we go along, you'll see we meet all of these objectives. Okay, so the author says right here, section 5.2 in the introduction of the first paragraph, he mentions that the mean, variance, and standard deviation for a probability distribution are computed differently from the mean, variance, and standard deviation for samples. Now, we should also say it's different from the mean, variance, and standard deviation for populations as well. The key is not whether it's for samples or whether it's for populations. The key, in my view, is whether we're talking about data that has already been measured or are we talking about what's happening in the future? What do we expect to have happen? Okay, so this section here, 5.2, is going to talk about those three things, and then we're going to have a new concept, a new measure called the expectation. All right, so the mean. What do we have for the mean? In chapter 3, the mean was very simple. X bar was summation of X. That means add up all of the values, all of the data points, whatever it happens to be, add them up and divide by little n. That was for the sample mean. For the population mean, same concept, add them all up, and then you divide by big N, where n is the number of points, data points in the entire population. So we always wanted to have this easy way of distinguishing. If we're talking about X bar, we're talking about a sample mean. If we're talking about mu, we're talking about a population mean. Okay? All right. So here's his question to you. Here's the motivation behind this. How would you compute the mean of the number of spots they show on top when a die is rolled? Well, you could try rolling the die, roll it 10 times, find out what you get. Okay, that would be taking a sample. It's a sample because the true population would be an infinite number of rolls. So you could roll it 10 times, you could compute the X bar. Okay, but what if you did it 50 rolls, 100 rolls? Okay, well, you're going to get better and better approximation of what the truth is. How many times do you have to roll it to get the exact answer? Well, if you think about it, it would have to be rolled an infinite number of times. Well, that's impossible. We can't roll it an infinite number of times. So what we're going to do instead is we're going to do the probability distribution. We're going to infer, we're going to use our brains to figure out what is the probability of this happening. Instead of taking actual measurements, we're going to say, well, I think we can figure this out using common sense and mathematical concepts, okay? All right. And then what he's talking about here is we got to have a new way of doing this. And what this does is it gives us the exact theoretical value of the mean. And we're basically saying, well, if it were possible to roll the die an infinite number of times, this is what you would get. Now, we know you can't possibly do that. But the concept is that if you rolled it a bazillion times, you rolled it 10 billion times or 2 trillion times, well, you'd get closer and closer to rolling it an infinite number of times, and this would be a better and better estimate. But we don't have to do that. We don't have to roll it 2 trillion times. We're smart enough to figure out what it's going to be. So it's a theoretical thing, but we are pretty darn sure that we're right, okay? So what the author is doing here is he's saying, well, before we actually write down the formula, let's not just write down formulas and memorize formulas. Let's think about it. So before the formula is stated, we're going to talk about an example. Okay, so we got 2 coins. So you either have 2 coins or you have 1 coin and you flip it, 2 times in a row. So you have the 2 coins, you toss them repeatedly, the number of heads that is recorded, the number of heads that occurred is recorded. What's going to be the mean of the number of heads? Now, you could do this a bazillion times, like I said, and we could compute it just like we did before, but let's think about it in a different way. So what's our sample space? Our sample space is you can get a head and a head and a tail and a head, and a tail and a head, a tail and a tail. So each one of those has a probability of 1/4. Now, why is that true? Why is it that each of these outcomes, now in this case, the outcome is 2 coins. So don't be misled. Don't think that, well, an outcome is flipping 1 coin. The outcome is flipping 2 coins. So each outcome has a probability of 1/4. In other words, the probability of getting a head and a head is 1/4. The probability of getting a tail and a head is 1/4, and so forth. Now, do you see why? It's because the first time you flip, the chance of getting a head is 1/2. The second time you flip, the chance of getting a head is 1/2. Well, similar remarks apply here. On the first flip, the chance of getting a head is 1/2. And then on the second flip, the chance of getting a tail is 1/2. So every single one of these is 1/2 times 1/2. So any one of these that you pick, the probability of getting that exact outcome is 1/2 times 1/2, otherwise known as 1/4. Okay, so what would you expect in the long run? In other words, if you did this a bazillion times, what you would expect is what we just said, that you'd have a probability of 1/4 for each of those outcomes. Okay, so now what the author is trying to do next here is he's trying to use this simple example as a way to motivate us for why do we come up with the formula that we come up with. So he's saying, well, in the long run, you'd expect 2 heads to occur this various number of times. Or I'm sorry, you would expect the 2 heads to occur 1/4 of the time, 1 head to occur 1/2 the time, and so forth, okay? So on average, what would you expect on average the number of heads to be? Okay, well, you can either have 2 heads, or you can have 1 head, or you can have 0 heads. Well, what's the chances of getting 2 heads? 1/4. Why is that? Because 1/4 of the time you're going to get HH, head, head. 1/2 of the time you'll get at least 1 head. Or I'm sorry, I shouldn't have said at least. Strike that. You would expect to get 1 head should occur half of the time, okay? 1 head. What the heck do we mean by 1 head? 1 head is here, HT, and here, TH, okay? So to get exactly 1 head, you can get it this way and you can get it this way. So 1/2 of these outcomes gives you exactly 1 head. Here's a head, here's a head. Here's 1 head, here's 1 head. That's 2 out of the 4 possibilities gives you the 1 head. So 2 out of 4, that's 2/4, that's 1/2. So that's where we come up with this. 1 head is going to occur 1/2 of the time. That's head tail or tail head. We're going to get no heads. In other words, right here, that's no heads. No heads will occur approximately 1/4 of the time. So on average, How did we do this before? Do you remember? The way we did this before with sample sizes or with sample statistics is we would take the probabilities and we would add them up, or I'm sorry, we would take the total number of outcomes, add them up, and then divide by the sample size. So that's how we did it before. We would just count them up and do the arithmetic, right? Well, now we're doing it a little bit different way. And he seems to think, the author seems to think that this is intuitively obvious. I don't think it's very intuitively obvious, but I'm going to go with the flow here, and we're going to see here in just a second, we're going to see the formula, how it works out. So what he's saying is, on average, over a long period of time, or long number of trials, you would expect the number of heads to be, well, there's a 1/4 chance of getting 2 heads. There's a 1/2 chance of getting 1 head, and there's a 1/4 chance of getting 0 heads. So you multiply these guys together and add them up, and you get 1. Now that's not so intuitively obvious to me. I think I can work it out, but it's just not that clear to me why that is true. It's not obvious. Let's put it that way. So if you're having a hard time seeing that, don't feel like the Lone Ranger. Okay. So what he's saying here is that if it's possible to toss the coins many times or an infinite number of times, the average of the number of heads would be 1. So how do we do this? To find the mean for a probability distribution. So we're not talking about a sample set now. We're not talking about actual measurements. We're talking about a probability distribution. What you've got to do is you multiply each possible outcome by its corresponding probability and find the sum of the products. So the mean, if it's a discrete probability distribution, is x sub 1 times the probability of x sub 1 plus x sub 2 times the probability of x sub 2, and so forth, all the way up to x sub n. Now, like I've told you before, don't be intimidated by these little subscripts. These little subscripts are merely intended to tell you, this is the first guy I'm talking about, this is the second guy I'm talking about, this is the third guy I'm talking about, all the way up to the final guy, which is x sub n. And then the p of x sub 1, p of x sub 2, that just tells me that's the probability of that first guy, the probability of the second guy, and so forth. So add all those guys up. Here's our notation that this author is using. It's the summation of x times p of x. He's just saying add all these characters up one after another. Okay. All right. So that's what he explains down here, and this tells you to sum it up. Okay. Now there's going to be a rounding rule. There's always a rounding rule. I never have them memorized, but you might have to memorize them. Okay. So go ahead and read this. Okay, the concept is that these measures, the mean, variance, and standard deviation, we're going to round them out. We come up with an answer. We round them out, or we round them one more decimal place than the number of decimal places in these outcomes that we're talking about. Okay, so we're ready now to talk about example 5.5, but let me do that in the next video.